Hi everyone, in this video segment we are going to be talking about acid-base conjugate pairs, okay? Conjugate acid-base pairs. This is a really important idea. Now, we're going to use NH3 as our reference molecule. The conjugate acid of NH3 is NH4. To make your conjugate acid, you are going to take your atom, your nitrogen atom, and you are going to add a proton. And as you bond it to another proton, that nitrogen no longer has its lone pair. So we could say we are going to add a proton and lose a lone pair to go from a molecule to its conjugate acid. This is to say, to become its conjugate acid, NH3 had to act as a base, meaning if we had hydrochloric acid, NH3 would share its lone pair with the proton, bonding to the proton, or hydrogen atom, to become the conjugate acid. So if we're looking at something's conjugate acid, we are saying this molecule has acted as a base to become its conjugate acid species. It has added a proton and we've lost a lone pair. Now, we could also imagine NH3 acting as an acid, losing a proton to become its conjugate base. So again, let's take an example. You might have something like CH3-. This is a very strong base. If it were to share its electron density, the negative carbon atom, with the proton, we could then deprotonate the nitrogen atom. And so the conjugate base of NH3 is NH2-. NH2-. Notice that to go from our reference molecule NH3 to its conjugate base, we have removed a proton and we've added a lone pair to the nitrogen atom. There's two lone pairs now, there was one to begin with. And I think this is really crucial too, just in terms of you understanding the aeroflow. The CH3- is sharing electron density with just the proton, and it is pulling the proton off of the nitrogen atom. And there are two electrons in the bond from the nitrogen to the hydrogen, the sigma bond. But the methyl carbon, CH3-, is just taking the proton, and so those two electrons are actually left on the nitrogen atom. That's why we have to show two arrows in an acid-base reaction proton transfer step, because the base is only taking the proton, but the two electrons in that bond need to go onto what we could call the acidic atom. Here's the acidic proton, here's the acidic atom, and it gains that lone pair. So we have removed a proton and we've added a lone pair to the nitrogen to form its conjugate base. NH3 acted as an acid, donating a proton to CH3- to form its conjugate base. All right, you could look at an example like water. Okay, water's conjugate base would be OH-. All right, so water, let's redraw water real quick. Water is H2O. The oxygen has two lone pairs. To draw its conjugate base, we think about removing a proton and adding a lone pair. And in the process, we become negative. The oxygen atom becomes negative. If you looked at water's conjugate acid, we would then add a proton to the oxygen and lose one of the lone pairs. So the conjugate acid of water is hydronium, H3O+, and we have added a proton to that oxygen atom, and we've lost a lone pair. And it's not that we lost the lone pair, it's that we used the lone pair to bond to the proton. If you had water and hydrochloric acid, the water molecule, the oxygen atom, would share its electron density with the proton, bonding to it. And so those two electrons are actually now in that bond from the oxygen atom to the proton that we've taken on. Okay, so I really encourage you to maybe watch this video over again, just because conjugate acid-base pairs are very important. And I know the term conjugate isn't an entirely descriptive word, right? So get these definitions down. You do want to be able to think about a molecule, like we talked about here with NH3, as being able to, in some cases, right, act as an acid or a base to form its respective conjugate species. Okay? Get the definitions down, and now we'll be going into quantifying acid-base strength.